Hello everyone, my name is Calvin Joshua G. Silvestre, and today we'll be dealing with Act 6, Torque, Power, Speed, Regulation, and Efficiency of Self-Excited DC Series and Shunt Motors. First of all, we head to LVSIM, and we have to set up our experiment. So first, we set up the mobile workstation, and the required equipment for this is a DC motor generator, then a prime mover, then a power supply, and the data acquisition module. Once everything is inside of the mobile workstation, we have to wire everything up. Now that everything is wired up, we can now continue with our experiment. So first things first, we have to put in the belts for our prime mover and the motor. So first we have to lower the front panels, making sure that everything is turned off. We click this and attach the belt from the prime mover to the motor, and then close all of the panels. Now from here we have to check what voltage and current rating the motor is allowed to handle. So right here we can see that it's 120 volts at 2.8 amps. So now we have to set our power supply to be able to provide not more than 120 volts at 2.8 amps. So we have to use our voltage control knob. Here we'll just be setting it to 60. Make sure that that's set correctly. Then now we have to turn on our power supply by clicking the switch here, and now we can see that everything is spinning. We have to turn this on as well so that our prime mover slash dynamometer has a readout. Now from here on we should have our notes handy. The important values that we need are the voltage knob percent, the current E1 voltage, the I1 current, and the RPM and torque values. So for the voltage and current, we can check our metering tab right here, and we hit refresh. So as for the current, we have 1.32 amps, and for our voltage, we have 85.02 volts. For the voltage knob, it is at 60%. The RPM of the prime mover is at 2213, and the torque is at 0 Newton meters. Now another thing to keep in mind is how the motors are spinning, and right now we have it spinning to the right, or in a clockwise orientation. After this we have to change our prime mover into a dynamometer and then record the results. So that can be done by flipping this switch right here and adjusting the load by this knob. We now have set it to 50%, and now the rotation stays the same. The rotation is going in a clockwise direction, but the torque is now displayed at 1.63 Newton meters. The speed is now slower at 631 RPM, and as for the voltages, we can go back to our metering tab and refresh it again. We have 81.25 volts, but now we have a current of 3.834 amps. With these values, we can go ahead into our calculation. Okay, so with all of our values recorded, we can now head to our calculations. Right now would be a very good time to have a scientific calculator on hand if you are going to follow along. So the first question is, what is the horsepower rating of the series motor according to the data recorded? So the formula for the horsepower can be derived from the torque formula, which is torque equals 44760 multiplied by horsepower all over 2 pi multiplied by RPM. So our torque from T1, the first recorded values, is 0. So 0 torque equals We have all over. We can use all over, which is 44760 multiplied by the horsepower, which we can put as x, divided by 2 pi multiplied by the RPM we recorded, which is 2220. And we can now find x by using shift solve for x, and x equals 0 because our torque is equals to 0 at the beginning of the recording. But now we use the T2 values, which gives us torque is equal to 1.63 Newton meters. Oops, there we go. While the RPM is now limited to 631. Now if we calculate our result, we get a horsepower value of 0.1443 horsepower. So that is the horsepower for the series motor according to our calculations. For the next question is, what is the efficiency and its speed regulation of the series motor using the data recorded? So we have two formulas in one question. So first of all, let's deal with efficiency. So the formula for efficiency is power out divided by power in multiplied by 100%. Now we can find power out and power in by multiplying the current and the voltage. But so we can then simplify our formula into power out. So let's say efficiency equals power out, which is the horsepower value that we solved from earlier, which is 0.1443 divided by 0.1443 divided by the input current and the input voltage. So the input current is 3.834 amps for our I2. 3. Okay. Okay, it doesn't allow us to put in the period. 3.843 amps multiplied by the voltage, which is 85 volts. I mean 81.25 volts. Okay, that's a bit weird. For some reason it's not allowing me to add the period, so our calculations are going to be incorrect if this is the case. Let's just use a different calculator. So 0.1443 all over 3.843 multiplied by 81.25, we get a efficiency multiplied by 100%. We forgot to multiply by 100%. Just imagine there's a period here to denote our current value. And now we have 74 over 160, 125. So that's about, I think I made a mistake. So it's about 0.046% efficiency. So that is very, very low. And with that, we can now switch off our main power supply and continue on our next experiments. Alright, switch everything off. And now the motors come to a stop. Okay, so as we continue our experiment, we have to redo all of our wiring. So for me, it's much more easier to just start on a new slate and get back to the mobile workstation, put in all of the equipment again, so the DC motor generator, the prime mover, the power supply, and the data acquisition module. Put everything back in, and then follow the new wiring diagram for our next experiment. Okay, so now that we have our new experiment fully wired up, we can proceed to our data gathering. So first of all, we have to turn on the main power supply, and oops, we have to turn on our main power supply. It's mostly the same setup as earlier, just wired up differently. We've powered on, and we now see the motors and the prime mover spinning. So now we have to record the voltage, current, RPM, torque, and the percentage of the voltage knob all over again. So we can go back to our metering tab for this. So the metering tab shows us an E1, so voltage 1 of 114 volts, 114.6 volts, I1 of 0.943 amps, I2, which is our secondary current, 0.432 amps, and we now go to read our RPM, which we can see is 1,263 revolutions per minute, and the torque is of course at 0 Newton meters, and of course we have to get our voltage knob again, which we still kept at 80%. Alright, now from here on out we can proceed to our next portion of the experiment. So question 17 is, as observed on the shaft of the motor and the dynamometer, what direction does the rotor rotate? So as you can see here, it's still going clockwise, so to the right. Next we can now flip the switch on the dynamometer to turn it, flip the switch on the prime mover to turn it into a dynamometer. And then we have to record all of the voltages and currents all over again. So now we switch it over and increase the load. Let's put it up to 50% again, as we did earlier. And now we can see that the torque immediately changed. So T2 now is, the torque 2 is 1.6 Newton meters, and the RPM is at 1027 revolutions per minute. We have to go back to our metering tab for the current and voltages. So we take the E1 again, which is, we have to refresh it again. E1 is now 110.4 volts. The I1 is now 3.721 amps, I2 is now 0.417 amps. And of course, the voltage knob hasn't changed at all. It's still at 80%. Now, we can, with all of these recorded, we can now proceed to our calculations. Alright, so now that we have everything recorded, we can go back to our calculations. The first question is, what is the horsepower rating of the shunt motor according to the data recorded? So the same formula as earlier. We have torque equals to 44760 multiplied by horsepower divided by 2 pi multiplied by RPM. So we put all of our values in. So we have the torque value of 1.6 Newton meters. Right now we put in 1.6 Newton meters is equal to 44760 44760 multiplied by X, which is the horsepower value, divided by 2 pi RPM. So 2 pi, and our RPM was at 1027. So 1027. Now we hit shift solve. Solve for X. We get 0.23066 horsepower for the shunt motor. As for the T0 value of 1263, shift solve, and we get a horsepower value of 0 because we have 0 torque. So that's for the first question. The second question is, of course, what is the efficiency and its speed regulation for the shunt motor using the data recorded? So same as earlier, we have the formula for speed regulation, which is, oh, I forgot that. So we have the formula for the speed regulation, which is RPM no load divided by minus RPM full load divided by RPM full load multiplied by 100%. So first we have the no load RPM, which is 1263. Okay, 1263 RPM minus full load RPM, which is 1027. This is divided by the divided by the full load RPM, which is 1027, then multiplied by 100. So the speed regulation is 22.979, and the next question is, what is the efficiency? So the same formula as earlier. We have the efficiency equals to P out over I times V. So the P out was the horsepower value we found earlier, which is, I forgot, so we can just redo the calculations. So the horsepower is equal to torque, which is 1.6. 1.6 equals 4760 44760 44760 multiplied by X and divided by 2 pi RPM. 2 pi RPM, which is 1027. And shift solve for x, we have this is division, and this is multiplication. Put this here, and we redo the shift solve. And yeah. We have 0.2306, which is our output power, that we can now use for the efficiency calculations, which is P out divided by IV, so we have 0.2306 divided by 0.2306 divided by current and voltage. So the current was 3.721. The current was 0.417. Yeah, it just doesn't want to let me press that, huh? 0.417 plus 3.721 multiplied by 110.4. So we have 2306 divided by 0.417 plus 3.721 multiplied by 110.4. We have 5.0477. So I feel like that's way too high. We multiply it by 100%. So yeah, we have 5.61% efficiency. So that is all for activity 6, and we'll move on to activity 10.